Hi there. I'm going to be talking a bit today about finding causes of build non-determinism in Bazel. So first, a bit about me. My name is Samuel, and I work on the mobile developer experience team at Square. And over the past year, we've been working on migrating our builds from Xcode over to Bazel, and that migration is what's inspired this talk. Bazel is an awesome build system. Bazel promises both performance and correctness. And honestly, what more could you ask for in your builds? But the fact is, fast and correct are both highly related to each other, and Bazel would be unable to deliver one without the other. So what does it mean for a build to be fast? Well, when you do a clean build, you download the source code for the first time and run build for the first time. You don't want to do any unnecessary work. And similarly, when you change a single source file and run build again, you still don't want to do any unnecessary work. And you want to be able to use all the cores available on your machine, or even better, on someone else's machine that you're able to run compute on. And last, but certainly not least, like any good programmer, you just don't want to do work when it's avoidable. Don't run things that don't need to be run to finish the build. Now, correctness is a lot simpler to define. Correctness from a build system simply means that given the same inputs, you're going to produce the same outputs. And Bazel's entire design is based around these principles. Fast and correct are not only goals, but they're core assumptions made in Bazel, and they help reinforce each other. So fast, how do we get there? Well, first off, we want to cache artifacts as much as possible. When you compile a source file, you want to take the outputs of that and save them. So when you go to compile the same exact source file again, well, you can skip doing the work because you already know what the output is going to be. And those artifacts, you want to cache them locally for the benefit of your future self. You also want to cache them remotely for the benefit of your teammates or build machines that you may have running. So now we're going to try and motivate why we care about deterministic, aka correct builds. And it's because of this caching. To be able to use cached artifacts, and now here's a fancy computer science term warning, builds in Bazel are Merkle trees, which is a fancy way of saying it's checksums all the way down. So to be able to use cached artifacts, all the inputs in that Merkle tree need to be the same. Bazel's caching is entirely dependent upon file checksums, SHA-256 checksums to be precise, rather than the timestamps that a lot of local-only build systems, such as Make, use. Now, caching in Bazel works on two levels, and I hope you'll forgive this quick digression as to how caching works. And this explanation holds for both a remote and a local cache. So the first level is the action cache. Bazel will look at each action it would want to run and compute its hash. This hash contains the definition of the action. Think the environment variables that it uses, the list of output files it's going to create, the command line to actually run the action, and also a combined hash of all the input files to the action. And when you get a cache hit, the action cache will tell you what the digests of the outputs are, so you can go and look them up. Where are you going to look those outputs up? In the content addressable storage. The CAS is much simpler. It's called content addressable because the cache key for each object is derived, you guessed it, solely from its content. And this helps make it resilient to hash collisions, and it also makes integrity verification really easy. Another benefit is that if the same file shows up multiple times in your build, it can share a cache entry. And one place where this comes up really, really frequently is with the empty file. It turns out that file is everywhere in everyone's builds. So you might be thinking, thanks for the background, Samuel, but I'm not exactly sure why I'd care. Where's the problem? And, well, it's not really a problem, but Bazel's model requires that the content of each output be deterministic. This is a gross oversimplification. Bazel can work just fine with non-deterministic outputs, but you want fast and predictable builds, right? Right? So here's a really simple example of a non-deterministic action. This is a gen rule that is valid according to Bazel. It'll even work with sandboxing enabled. But if you get Bazel to run it twice, it'll give you two outputs for the same set of inputs. In this case, it's the empty set of inputs. Now, there are a couple of common sources of non-determinism that I've run into over and over. The first one of them is random numbers. It shouldn't be much of a surprise that randomness is kind of the enemy of determinism. The next is sorting of hash maps and dictionaries. Many programming languages use random sorting of dictionaries. And so when those dictionaries get written out as outputs, their contents can be jumbled from run to run. Another common source of non-determinism is timestamps. When we talk about running multiple builds, we mostly mean builds run at different times. And so if you run multiple builds, the timestamps that can get embedded into output files will be different. And finally, incorrect rule implementations can lead to non-deterministic builds. A really common example of this is if you have sandboxing disabled and one of your actions uses a file that it hasn't declared as an input. Bazel won't know about that. And so it might run actions in different orders, and you may end up with different results. Now, that one's not really Bazel's fault. The fix there is sort of fix the rule implementation. So cool. We now know that there's a bunch of ways to make a build non-deterministic. But knowing that it's possible in a build is different from finding out where it's happening and putting a stop to it. But how can we tell when it's happening? Otherwise, we'll just suffer a broken build for approximately forever. And take my word for it, that's no fun. A couple of common symptoms that will point to a non-deterministic build have to do, unsurprisingly, with caching. The first is when we see a cache just keep on growing. We keep running builds in the same commit over and over and over, and the cache keeps growing. Similarly, we can see that rebuilding the same commit is running actions over and over again, even though the build action output should be cached. Now, the last way would be the best, but unfortunately it isn't as easy as it should be. Bazel could just tell us somehow, magically, that our build is non-deterministic. It doesn't, but fear not. Bazel actually has all the tools you need to figure it out, and we're about to walk through how to stitch them together. So to get started, we're going to want to set up a cache. Not to make our builds faster, though this work will help in that department too, I promise, but so we have a good place set up to store all the artifacts we're about to generate. Now, unfortunately, doing this investigation is going to require some bespoke configuration. By default, Bazel doesn't spit out all of the info we need, nor behave in the way we need. Now, this is actually a good thing. We don't want to do full builds all the time. We don't want to generate massive logs all the time. But for this particular investigation, we're going to need to configure Bazel to do just that. So now that we've done the configuration, it's time to build. We're going to want to start off by running a Bazel clean -- expunge. We want all of our actions to get executed. And yes, I promise this is one of the few times that anyone is going to tell you that you need to do a Bazel clean. So we're running our build. Go grab a nice cup of tea. If your project is anything like ours, you're going to be building a very large application and have to wait maybe around half an hour. And when you come back, your build is done, remember to save the experimental execution log file that you just configured Bazel to generate. This is the file we're really after. It contains a record of every action Bazel has executed, along with some details about that action. So that exec log file contains the environment variables, the command line, the input files, and the output files of every single action that Bazel has run in your build. It's a super handy tool, and you can also use it to tell you if you're invoking things with, let's say, different command lines on different platforms or something like that. But most importantly for us, we'll be able to use it to tell when inputs and outputs of actions have different contents, aka when our build is non-deterministic. So now we're going to build again, and yes, we're going to need to clean first, and we're also going to need to change the remote instance name so we can tell the cached artifacts from our two different builds apart. So we come back, and we now have two massive exec log files. You did remember to save the first one, right? Now, if you were to go and crack them open right now, you'd find that they're binary files. They're not the easiest thing to diff. And here, Bazel swoops in to save a day. There is a built-in tool to parse these logs. You'd never have guessed it, but it's called the exec log parser. Now, this is the tool that I use to convert that log file from a few slides back into text. You can feed it one of those binary log files, and it'll spit out a plain text conversion for you. But the parser has one last trick up its sleeve, and we saved the best for last. If you pass in not one, but two binary exec logs, the exec log parser will spit out two plain text files with the actions in the second text file reordered so they match up with actions in the first file. Now, when running this, you may need to give the JVM a ludicrous amount of RAM. It required like 20 gigs to run in our repo, and I had to do some Googling to figure out the magic JVM flags to make that work. But after it chugged away for a little bit, we had a large plain text file. We actually had a pair of them. And because we have a pair of files and they're plain text, we can diff them now. We can use the plain old diff command to show what's happening. Now, this is going to work best when most actions between the two builds are the same. Otherwise, the plain text diffs might not have enough anchor points to not be all jumbled up. And running this diff command will output a combined log for us that'll contain the contents of both logs, but with a prefix denoting the build number on lines where there is a difference between the two log files. So this diff is going to be massive. Scrolling through it won't be very helpful. It can be like 10 gigs of text. So I did what any good lazy programmer would do, and I wrote a script to go through this and group the actions that had differences in them by their mnemonics, and sort of point out which rules essentially had issues. So I threw up on my GitHub account a V2 of the hacky tool I built to help me read through these diffs. I originally wrote it in Ruby and then decided it would be fun to stretch my Rust muscles, because Rust is supposed to make everything go faster or something like that. Now, warning, this is not production code, but hopefully it's a helpful example of the ways you might want to dig into these diffs yourself and can help point out places where you frequently have actions that are non-deterministic or have non-deterministic inputs. Now, I say non-deterministic inputs because it's non-deterministic inputs that can really poison your build and force you to rerun actions over and over and over when using a cache. Yes, ultimately, it's the outputs that are different, but depending on where that output then gets used later on in the build will determine how big a deal that is. If an output is different but doesn't get propagated to intermediary targets as an input, it won't really poison the build as much. So we've run the tool, we've found an action that has differing inputs and differing outputs, and now we want to see where the difference is coming from. So we're going to download the files that are used as inputs but have different contents. This is where setting different remote instance names can be helpful. So in our cache, we can tell which build the different files have come from. And now we're going to want to diff these different files. And this is where your domain expertise can come in. You know the different files that your build is producing. So I'm really familiar with iOS builds. So I'm looking with tools that I'm already familiar with to inspect these files. So looking at object files, I'm running the strings command or nm or otool to figure out what their semantic contents is, and then running diff based on this snippet against the two of them. So I could use my knowledge to figure out where those differences were coming from. Oh, cool. Neat trick, Sam. I'm glad you got your build to be deterministic. But what else is this sort of approach useful for? Kind of the sky's the limit. You can use it to compare runs of your build on different machines, in different environments, or with different tool chains. Now, here are a pair of really quick examples of findings that I had going through our build. Both of these come from the rules Apple rule set that are used for building iOS apps. But I'm sure there are similar stories for all sorts of different rule sets. The first was the storyboard link action in the resource rules in rules Apple. What this does is it takes nib files that have been compiled and links them together. And what we found was every single time this showed up in the execution log, the inputs were always different. And downloading those inputs, we could see that things were jumbled around. The files looked mostly the same, but different blocks of the binaries were reordered. And diving in a bit further, we could tell that this was because it was serializing dictionaries that had non-deterministic ordering to them. And so because we couldn't go and fix the tool that does the storyboard linking or the nib compilation to be deterministic, because those are in Xcode and we don't control them, we sort of threw our hands up and said, okay, there's nothing we can do. We'll continue to cache these things, continue to allow them to run remotely, because these outputs aren't used for any other compilation. They're only used for bundling the final application. Now, the second example is from the imported dynamic framework processor action, again from rules Apple. And what this does is it takes dynamic frameworks that you're importing and packages them up into a zip before then processing it. And what we were seeing is that those zip files were different, even though the inputs to them were always the same. So we downloaded the zip files and diffed the output of running unzip-v on them. And what that showed was that the timestamps in the zip were different for directory entries, but they were the same for file entries. Now, the good news was we could go and fix this And indeed, I sent a pull request into Rules Apple to set a consistent timestamp not only for file entries, but also for directory entries before creating the zip. I'm sorry that I couldn't come and give you a magic experimental Bazel flag that would go and make all your builds deterministic. But hopefully I've helped motivate a bit why deterministic builds matter, and shown a bit of the ways that you can figure out where your build is non-deterministic, and really dive in so you can go and fix it. And hopefully, moving forward, the common tool chains that we all rely on for builds will default to being deterministic by default without us having to set special flags or environment variables or do post-processing to make them be that way. But until then, we know what work we have to do. So I hope you've enjoyed this talk, and I hope you have a nice day. Thank you.